Hey everyone, my name is Dan the Tutor, and today we're going to be continuing our talk on Calculus AB, and we're going to be looking at continuity today. So to just give a brief description on what continuity says, continuity is where the function is continuous. Well, what does continuous mean? As far as you're concerned, continuous means you're able to draw the function without lifting your pencil. And if you can draw the function without lifting your pencil, it's continuous. So let me give you an example. We're talking about continuity. Let me give you an example. Let's say we have here some graph that looks like this, x, f of x, and it looks something like this, a parabola facing downward. My question for you, where is this function continuous? You would probably say it's continuous on negative infinity to infinity, right? That's where you would say it's continuous, and you would be correct. Why? Because you can draw this function from negative infinity to positive infinity without lifting your pencil. I mean, I just did it right here without lifting my pencil, so it's definitely possible. Now, what if I told you there was a hole in the graph at this point right here, at some point A? Now is it continuous? I think you can tell something's fishy here. It's probably not going to be continuous. It will not be continuous, and the reason is because we have a hole in the graph. If we have a hole in the graph, then we have to, lift our pencil as we're drawing the line here because it doesn't exist at x equals A. Now, follow-up question, there's a hole in the graph. What if we filled in this hole right here? So now we have a value at x equals A, it's down here. Now is it continuous? It is not going to be continuous. Here's why, because I'm still drawing my function, and then I still have to lift my pencil and draw it down here, and then finish drawing my function. So that's not continuous. The only time it's going to be continuous is when there's no hole in the graph. In other words, that has to be closed. It has to be closed everywhere. Function has to exist everywhere. And if it doesn't, then what we can say is it's continuous on some kind of region. And the region here would be negative infinity to A, parenthesis, comma, parenthesis, A, comma, infinity. And here's what this is saying in math speak. From negative infinity to A, not including A, right? Parenthesis means don't include. If I wanted to say include A, I would put a bracket there. So since it doesn't include that point, it's a parenthesis. And then again, from A to infinity, not including A because there's a hole in the graph at A. An example of when you would include A would be this example here where we have, again, some graph, x, f of x, and then we have some kind of point like this, closed circle, open circle, continue. So in this example with A, this is also not continuous because we have that jump discontinuity here. And what that would look like then is negative infinity to A, close bracket because we're including the point A from the left side because of the closed circle, comma, A with a parenthesis, comma, infinity, and that gets the parenthesis because it has a hole in the graph, open circle, don't include A there. And that's how you can think of continuity when looking at a graph. And now things get interesting, however, when we start thinking about continuity in terms of not a graph, but a function. It's a little bit more difficult. And when we're talking about that, we're really talking about continuity at a point. Continuity at a point. And how we can prove if there's continuity at a point when we're given some function is three things need to be true. We're going to be doing these three things every single time. The first thing, we need to prove that f of A, that point A we were talking about earlier, that point has to exist. In other words, it has to be a closed circle. If it's an open circle and there's no, actual value for f of A, it's not going to exist. So f of A has to exist. The value of the function has to exist. That's what I'm trying to say. Then we need the limit as x approaches A, f of x, to exist. And the only way that's going to exist is we need to talk about a concept of the left and the right hand limits. So what a left hand limit is, limit as x approaches A from the left, which we denote with a minus sign. The minus sign just means left, and then some function f of x. And if we wanted to say what the limit is approaching from the right side, we would say limit as x approaches A plus for right, f of x. And again, that plus sign means right. And in order for the limit to exist, these two things have to equal each other. Okay? If the left-hand limit does not match the right-hand limit, the overall limit is not going to exist. So we need those two limits to match up. And if they do match up, and we've met our first two conditions, It's still not continuous yet. The only way it's continuous is if f of a, the actual value of the function, is equal to the limit at that value. And if this is true, then the limit exists. So first of all, we need to find the actual value of the function, then we need to find the limit at that value, and then we need to prove that they are equal to each other. And if we do that, then we can say the point is continuous. I know it sounds like a lot of work, it is a lot of work, but it is necessary to actually prove that the point is continuous. So let's look at an example problem. I want to know, is f of x equals x squared plus 3x plus 2 over x plus 1, is f of x, is that continuous at x equals -1, okay? So the first thing we would do, again, to prove that this is continuous, and by the way, this example is way too difficult to graph, don't try graphing it, and besides, we don't need to graph it. We have the skills that we can just deal with the numbers and prove if it's continuous. And the first thing we need to do is ask ourselves, is that point f of -1, does that point exist? And the way we prove that is by literally plugging in -1 everywhere and seeing if we get a value at the output. So we get -1 squared plus 3 times -1 plus 2 in the numerator. And in the denominator, we get -1 plus 1. And immediately red flag should be going off because we're going to get 0 in the denominator, and I can tell you that does not exist. The denominator does not exist because we're getting 0 in the denominator. And so therefore, we already failed our first condition. Our first condition was not met, which means we don't even need to go through steps 2 and 3. We're going to say not continuous. And now let's look at one more example, and this example is going to use a piecewise function, which means it's annoying. In case you've never seen a piecewise function before, it looks something like this. F of x is equal to something like x plus 2 when x is greater than or equal to 1, and then we can say something like 3x squared minus 1 when x is less than 1. And with any piecewise function, it's important to understand that it's just doing something different from both sides. And specifically what's going on here is that the function's changing at the point x equals 1. And so we could ask, is f of x continuous at x equals 1? That would be the question. So is it continuous at x equals 1? First of all, does the function exist at 1? What is the value f of 1? If I were to plug in x into this function, would I be dealing with the top or the bottom equation? Well, if we think closely, or if we think carefully, then we remember that the greater than or equal sign means that for the point x equals 1, we are going to be dealing with the top equation. And so I can plug in then 1 into the top equation. It's going to be 1 plus 2. We just get 3. And now we have, we passed our first check. The first check just proves, does it exist? Now for the second check, we need to see that the limit exists. That the limit as x approaches 1, f of x exists. And since it's kind of tricky here, we have a piecewise function, and if we remember, it's going to have different behaviors from both sides, and we need it to come to the same point from both sides in order for this limit to exist. And this is when we're going to be using the left and the right hand notation. So, limit as x approaches 1 from the left, f of x. Remember, if we think about what this function kind of looks like, something's going on at x equals 1. At x equals 1, it's going to be following the red. At any point x greater than 1, it's going to be following the red. It's going to be right of 1. And for anything with the green here, less than 1, it's going to be, using the bottom function. And so once you understand that, what we can do is recognize that the limit as x approaches 1 from the left of 1, it means that we're going to be looking at the green, since the green is left of 1. And how would we compute that limit? Well, for the most part, we can just use direct substitution in these cases, unless there is an example where it doesn't, compute. But we're good here. So we get 3 times 1 minus 1, 3 times 1 squared minus 1, which is just 2. So we have the left-hand limit, but in order for the limit to exist, the right-hand limit needs to exist, and it needs to equal 2 in this case, so it matches the left-hand limit. Limit as x approaches 1 from the right is going to equal f of x. And limit as x approaches 1 from the right, f of x, is going to follow the top equation, the red, because it's greater than 1, it's coming in from the right. So we're going to plug into x plus 2. So 1 plus 2, that is going to equal 3. And so right there, since the limit as x approaches 1 from the left does not equal the limit as x approaches 1 from the right, we can say that we did not meet condition 2, and the function is not continuous at that point. And really, if we're thinking about what's going on at this point 1 here, pretty much we know that it's approaching this point here, 2 from the left, and it's actually going to be an open circle there since it's the less than sign. It's approaching 2 there, and then it's approaching 3 from the right side, so it would be a closed circle at 3, and then whatever that function happens to look like. So in a very rough sense, this is what that graph looks like. And once you understand that, you can then start to think about it in terms of, oh, I see why the limit does not exist. They're approaching 2 different points from both sides. And that's exactly what's going on. And for that reason, it's not continuous. We're going to have to lift our pencil at x equals 1 in order to draw the whole line. And the only way it would be continuous is if they actually ended up at the same point and we could draw it. And so that's going to wrap it up for this lesson. Thank you for watching. My name is Dan the Tutor, and I'll see you next time.